Hello and welcome to Group 54's machine learning project on New York taxi fare prediction. Our team comprised of myself, Rohan Kapoor, Vin Kai Trong, as well as Min Tan Ko. All of us had an equal role to play in the project and the contributions that we put into it. Today we'll be going through a few things. First, we'll talk about a brief introduction or the impact of the project. Second, we'll go through the exploratory data analysis and feature processing that we used. Third, we'll talk about our model and the results that we obtained. And lastly, in conclusion, we will talk about some challenges faced and the lessons learned from them. So let's begin with the introduction. Today, there are more than $1.8 billion that are spent in the New York taxi industry, and 240 million passengers ride the New York cabs every year. There are 12,000 yellow cabs in New York that are currently operating, which means that this is a massive scale project that probably needs some attention. We think that finding out the fare by being able to look at the dataset and applying a machine learning model can be very helpful to a numerous amount of commuters as well as the city planners of New York so that they can make their trips more efficient. This can also be beneficial to the economy of New York and to the taxi drivers who need to be able to make their living wages. Therefore, this Kaggle competition, which was called New York City Taxi Fare Prediction, demanded us to build a model that predicted the total fare of a taxi trip in New York City. Let's talk about the exploratory data analysis and feature processing. First, on the data analysis. In total, this was a very large training dataset with more than 55 million rows. For the pickup timings that we had in this dataset, we analyzed them and used bivariate analysis to compare them in terms of how many pickups are done by each day of the week and how many pickups are done every hour of the day. As you can see in the graph above, for the weekday, you can see that the graph slowly increases up until Friday, and then on the weekends it starts to decline until Sunday, and then on Monday it starts to pick up again. This proves that on weekdays cabs are most popular. On the second graph, you can see that in terms of the hours, the most number of trips are taken between 6 and 7 p.m., which makes sense as this is mostly when office timings elapse. We also used k-means clustering to find out the busiest pickup and drop-off areas within New York. Unsurprisingly, we found that the Upper East Side and Manhattan, closer to the Central Park, were the busiest and most densely populated clusters from our dataset. We also analyzed the number of total trips that were taken throughout the year span of our dataset. We can see that this remains more or less consistent, with some fluctuations on the basis of some critical events. We also used an external dataset for the New York weather dataset to look at the temperature over time, as the temperature largely affects the number of taxi trips, which leads to more traffic. This could also happen when there are such things such as precipitation in terms of rain or hailstorm, all of which were incorporated into our dataset. The total fare amount as compared to each hour of the day came to be largest between 4 and 5 a.m. The conclusion or inference that we can get from this is probably that the price surges late in the night or early in the morning. Next, let's talk about feature processing. This involved two key steps: feature engineering and feature selection. For our feature engineering, we did a few things. We decomposed the timestamps that we had for our pickup date and pickup time, and we formed pickup and drop-off clusters on the basis of the latitude and longitude that we were given for each of these pickup and drop-off locations. We were also able to find exact distance measures by using things such as Haversine distance, Manhattan distance, and bearing direction. Furthermore, we imported the US holiday calendar dataset and looked at which of the days were necessarily holidays. We then compared this to our dataset to find out whether a trip was being taken near to a holiday within a few days of the holiday itself. This would likely mean that the fare is going to increase near the holidays, since there's a surge of people who take cabs during holidays because there are more people who are present at home. For the next part of our feature engineering, we also did some principal component analysis, where we were able to plot the variance of the data points using the red lines, as you can see, onto a particular flat line on a graph. This makes the feature easier to visualize and find relevant patterns and boosts the features for our model to be able to predict our test data set more efficiently, and it makes the ML model more efficient. Next, let's talk about the model used and our results. We finally ended up using XGBoost with k-fold cross-validation, which was a unique combination that led us to a very astoundingly efficient result. XGBoost is an optimized distributed gradient boosting library. We preferred it because it's been proven to be very efficient, very flexible, and very portable. And as for k-fold cross-validation, we use this to resample the process and to tune the hyperparameters within our data. Upon experimentation, we found that the best number of splits for our dataset was k equals 10, where we used 9 for the training in the model and 1 for the testing. The motivation behind using XGBoost was manifold. We feel that this was ideal for the regression-related predictive tasks, as has been proven in many research papers before. It has a high execution speed and model performance, especially when coupled with the GPU, and it's absolutely ideal for the sort of structured data that we have, which was cleaned and pre-processed data and not very messy. But lastly and most importantly, we think that this is sparse aware, wherein it takes care of outliers and doesn't necessarily try and include them within the dataset for the prediction, as it is a boosting model. The block structure of XGBoost also supports decision parallelization. This supports continued training, and XGBoost also has multiple hyperparameters such as the general, booster, learning task, command line, maximum depth, and many more. We feel that the k-fold cross-validation, because of these multiple number of hyperparameters, allowed for beautiful hyperparameter tuning for our model without any bias. We tried to experiment with a lot of other models, the details of which you can find in our report along with the relative performance of each of these models. But we found that the time consumption is extremely high for hyperparameter tuning and k-fold cross-validation in a lot of these other models. We also felt that they are more likely to overfit than other bagging algorithms like random forest aggressor. And the training time was relatively high for models such as CatBoost and LightGBM. We also experimented with deep learning and neural networks, as well as ensemble learning to be able to try and get a better RMSE. However, we found that the best RMSE was with this unique combination of k-fold cross-validation as well as XGBoost. How do we do the hyperparameter tuning? For the k-fold cross-validation, we had a very simple algorithm. We first shuffled the dataset randomly and split it into 10 groups. And for each group, we take that group G as the test data and other groups as the trained data. We then fit the model on the trained data, evaluate on the test, retain the evaluation score, and discard the model entirely. We continue to do this for each of the hyperparameters so that we are able to tune them in the most efficient manner possible via our k-fold cross-validation. The final hyperparameters for our XGBoost model look something like this, with a maximum depth of 11, the minimum child weight of 1, and of course the booster being the GB tree. So why did our particular model necessarily work so efficiently? We feel that there are 3 reasons why this was so efficient. First was because we were able to reduce the dimensionality of our variables during hyperparameter tuning. Secondly, the bias of our model had been reduced with k-fold cross-validation because we were able to sample and resample it multiple times. But lastly, by applying principal component analysis, we were able to auto-boost certain important features such as the distance between the pickup point and the drop-off point for a New York taxi. Let's move on to the results and how we actually performed. In conclusion, we had a root mean squared error score or RMSE of 2.91956. As you can see, this is how it appeared on our submission on Kaggle as well. This led to a leaderboard rank of 148, with us being in the top 9.9% of all submissions. Let's then talk about the challenges faced and the lessons learned. In terms of the challenges faced, there were quite a few challenges that we had to overcome. The first of which was resource consumption. For our resource consumption, we felt the machine learning and deep learning models require usually a high amount of computation power. Add to that the layer of complexity of our dataset literally having 55 million rows. Thus, we had to overcome this particular challenge by using cloud computational services like Kaggle kernels and Google Laboratory. The second challenge was about sourcing external datasets. Since the taxicab dataset that we had only had a few columns that we had to optimize, we had to use other external datasets such as the New York City weather. We also experimented with other datasets such as party datasets or OSRM distance datasets, but we found that they weren't exactly tailored to our liking and were not able to produce the best results. Pre-processing and merging the new dataset that we had was an arduous process that took us quite a lot of time. The third challenge was collaborative coding. For collaborative coding, we divided and conquered the task by assigning various unrelated or non-prerequisite tasks to our teammates. Some tasks had dependencies with others, so we had to use Google Colab. But Google Colab also posed issues when two or more members were working simultaneously, as the code would get overwritten while saving. Also, the Google Colab had a very short runtime and upon being left idle, refreshed the kernel, literally erasing a lot of our variables. The last challenge that we faced was the data management challenge. The variable that we were predicting, fair amount, only had a strong correlation with the distance variables, which was something that we were able to find out. The distance between these pickup and drop-off points was calculated using the Manhattan distance as well as the Haversine distance for the latitude and longitude. This was a difficult thing to calculate, but we were able to manage it in the end. Finally, onto our learnings. We had 4 primary learning outcomes from this particular project. The first was in terms of our machine learning competencies. We successfully implemented a multivariate predictor and learnt a lot about the XGBoost model. Second was about technical research. We researched various ML models, implemented them, found out why they had a poor performance, and understood their architecture to perform hyperparameter tuning properly on them. The third learning was obviously teamwork. It's not always easy to work in a team because some people are more busy than others at different points in time. Therefore, collaborating and being able to come together as a unit was something that we were able to pick up and learn in a very efficient manner at the end of this long project. But lastly, on critical analysis and roadblock removal, we had to come up with some very dynamic solutions to the roadblocks that we had discussed before and to the challenges that we had. The most important of which was loading such an important and heavy data set and being able to train the model on those many number of rows. We were finally able to accomplish this because one of us had a GPU enabled device and we also used the GPU on the Kaggle kernel to be able to make our model training a lot more efficient. All in all, this was a very fruitful learning experience for each and every one of us, and we thoroughly enjoyed the process. Thank you so much for listening and have a nice day.